Ladies and gentlemen, circadian aligned eating refers to the practice of consuming food in accordance with the body's internal biological clock, also known as the circadian rhythm. This rhythm is an approximately 24-hour cycle that governs a wide array of physiological processes, including hormone secretion, sleep, wake patterns, and metabolic activity. The central clock is located in the suprachiasmatic nucleus ascion of the hypothalamus and is primarily regulated by light exposure. However, peripheral clocks exist throughout the body, including in the liver, gut, pancreas, and adipose tissue, and these are especially sensitive to the timing of food intake. Emerging research in chronobiology has demonstrated that when we eat may be just as important as what we eat, especially in the context of fat loss. In particular, aligning food consumption with the body's natural rhythms can significantly enhance metabolic health, improve insulin sensitivity, and optimize fat oxidation. During the day, especially in the morning and early afternoon, the body is more metabolically active. Insulin sensitivity is at its peak, which means that cells are better able to uptake glucose from the bloodstream and utilize it for energy rather than storing it as fat. As the day progresses, insulin sensitivity naturally declines, making late-night eating more likely to result in fat storage rather than energy utilization. One of the mechanisms behind this involves the temporal pattern of metabolic gene expression. Certain genes that control nutrient metabolism, such as those involved in lipolysis, glycolysis, and mitochondrial function, are expressed more actively during the earlier part of the day. Eating late disrupts this expression pattern, essentially sending conflicting signals to the body. This misalignment between nutrient intake and the circadian rhythm has been associated with increased fat accumulation, impaired glucose tolerance, and even elevated markers of inflammation. Time-restricted feeding (TRF), a form of circadian aligned eating, involves consuming all meals within a consistent 8 to 10 hour window, ideally earlier in the day. This approach has been shown to enhance weight loss, reduce body fat percentage, and improve key biomarkers such as fasting glucose and insulin levels. Importantly, these benefits occur even when calorie intake is held constant, which strongly suggests that the timing of meals can independently influence fat metabolism. In rodent studies, mice fed during their active phase, which corresponds to the human daytime, maintained a healthier weight and metabolic profile compared to those fed during their rest phase, despite identical calorie intake. In human trials, individuals who ate the majority of their calories earlier in the day lost more weight and exhibited better insulin sensitivity than those who consumed larger meals later in the evening. These findings support the concept that front-loading caloric intake, having a substantial breakfast and a moderate lunch while keeping dinner lighter, can facilitate more efficient fat burning. Another key consideration is the role of melatonin, the hormone that signals the onset of sleep. Melatonin levels begin to rise in the evening and are inversely related to insulin sensitivity. Eating when melatonin is elevated, typically after sunset, can impair glucose tolerance and increase fat storage. This is especially relevant for individuals who snack at night or consume late dinners under artificial lighting, which can also disrupt sleep patterns and further compound metabolic dysregulation. In addition, gastrointestinal motility, digestive enzyme secretion, and gut microbiome composition all follow circadian patterns. Digestive efficiency is generally higher during the earlier part of the day, which means the body is more capable of processing and assimilating nutrients. Eating late may result in slower digestion, fermentation of undigested food in the gut, and increased production of endotoxins, all of which can contribute to systemic inflammation and impaired metabolic health. By consistently eating within a defined window that starts earlier in the day, say from 8 a.m. to 4 p.m. or 10 a.m. to 6 p.m., the body experiences a prolonged fasting period overnight. This fasting window not only gives the digestive system time to rest and repair, but also promotes autophagy, a cellular cleanup process that is linked to improved metabolic efficiency and reduced fat mass. Cold exposure, also known as cold thermogenesis, refers to the deliberate and controlled exposure of the body to cold temperatures for the purpose of triggering specific physiological responses. These responses can activate mechanisms that contribute to fat loss, metabolic efficiency, and overall hormonal balance. Among the most interesting aspects of cold exposure is its ability to stimulate brown adipose tissue (BD), a specialized type of fat that burns energy to generate heat through a process called non-shivering thermogenesis. Unlike white adipose tissue, which stores energy as fat, brown fat is metabolically active. It contains a high density of mitochondria, the cellular organelles responsible for energy production. These mitochondria are rich in uncoupling protein 1-UCP1, which allows energy to be released as heat instead of being stored as ATP. When exposed to cold temperatures, especially around 10-15 degrees C, 50-59 degrees F, the body activates BD in an effort to maintain core temperature. This process increases energy expenditure and leads to the burning of calories from both glucose and fatty acids, thereby contributing to fat loss. Cold exposure also leads to the recruitment and conversion of white fat into a more metabolically active subtype known as beige fat. Beige fat shares some of the thermogenic characteristics of brown fat and can be induced through repeated cold exposure. Over time, this transformation increases the body's baseline metabolic rate, meaning more calories are burned at rest. This adaptation, combined with other metabolic benefits, makes cold exposure a powerful tool for those looking to accelerate fat loss without necessarily increasing caloric restriction. Another crucial mechanism involves norepinephrine, a neurotransmitter and hormone that is rapidly released in response to cold. Cold exposure activates the sympathetic nervous system, leading to a surge of norepinephrine throughout the body. This chemical messenger binds to adrenergic receptors on brown and beige fat cells, stimulating the breakdown of stored triglycerides into free fatty acids, which are then oxidized to produce heat. This process, called lipolysis, is central to fat mobilization. Norepinephrine also enhances attention and mood, which is why many people report a heightened sense of alertness and well-being after a cold shower or plunge. In addition to norepinephrine, cold exposure impacts other key hormones involved in metabolism. It increases adiponectin, a hormone secreted by fat cells that enhances insulin sensitivity and promotes fatty acid oxidation. Higher levels of adiponectin are associated with lower body fat and reduced risk of metabolic diseases. Cold exposure has also been shown to transiently suppress leptin, a hormone that signals satiety. While chronically low leptin can drive hunger, acute decreases during cold exposure may be part of a broader metabolic adaptation to increase energy availability. From a practical standpoint, cold exposure can be achieved in various ways. Cold showers, ice baths, cold water swims, or even standing outside in light clothing during cold weather. The key factor is consistency and tolerability. Short durations, such as 1-5 minutes in cold water, typically below 15 degrees C, are often sufficient to stimulate thermogenic pathways. It's also important to consider the timing. Morning cold exposure can enhance wakefulness and align well with cortisol rhythms, while post-workout cold exposure may blunt some of the inflammation required for muscle growth and is better avoided immediately after resistance training if hypertrophy is a goal. Cold exposure also interfaces with mitochondrial biogenesis, the process by which new mitochondria are formed within cells. Repeated cold stimulus encourages cells to become more metabolically efficient by increasing mitochondrial density, particularly in skeletal muscle and adipose tissue. This results in improved energy utilization and endurance over time, which indirectly supports fat loss by enhancing the body's ability to oxidize fatty acids during both rest and activity. Another benefit tied to cold exposure is its potential to shift the body's fuel preference from glucose to fat. Research has demonstrated that after cold adaptation, the body becomes more reliant on fat as a primary energy source, especially during non-exercise conditions. This shift in substrate utilization supports long-term fat loss, as the body preferentially accesses stored fat for fuel instead of circulating glucose. Additionally, intermittent cold exposure may help regulate blood glucose levels and improve insulin sensitivity, further supporting metabolic flexibility. There is also a psychological aspect to consider. Cold exposure builds mental resilience. The discomfort associated with stepping into cold water trains the brain to tolerate controlled stress, which has downstream effects on motivation, discipline, and consistency, key behavioral components of successful fat loss. The dopamine surge that follows cold exposure also improves mood, energy, and the likelihood of engaging in further health-promoting behaviors. For you said, Zone 2 training expanded up to minimum 600 words and do not add any ending sentence, do not add bullets points, ChatGPT said. Zone 2 training refers to aerobic exercise performed at a specific intensity where the body primarily relies on fat as its main fuel source, rather than carbohydrates. It is categorized by maintaining a heart rate that is approximately 60-70% of one's maximum heart rate. This training zone is often described as being able to carry on a conversation comfortably while exercising. Despite being less intense than high-intensity workouts, Zone 2 training plays a critical role in improving metabolic flexibility, mitochondrial density, and long-term fat loss. One of the primary physiological benefits of Zone 2 training is the enhancement of mitochondrial function. Mitochondria are the energy-producing organelles within our cells responsible for converting fuel into usable energy in the form of ATP. When individuals consistently engage in Zone 2 exercise, the body adapts by increasing both the number and efficiency of mitochondria, especially in skeletal muscle. This adaptation allows the body to oxidize fatty acids more efficiently, even during rest. More mitochondria mean a higher capacity to burn fat for energy, which is a foundational mechanism in sustained fat loss and improved endurance. Zone 2 training also increases capillary density in the muscles, which enhances oxygen delivery and waste removal. This improved blood flow allows fatty acids to be transported more efficiently to the mitochondria, supporting greater fat oxidation. Unlike anaerobic training, which quickly shifts the body's reliance to glucose and produces lactate, Zone 2 training helps develop the body's ability to operate in a low-lactate environment. This minimizes metabolic stress and allows the body to maintain prolonged energy output with less fatigue. Over time, this improves the lactate threshold, the point at which lactate begins to accumulate in the blood, making other forms of training more efficient and effective. One of the distinguishing characteristics of Zone 2 is its impact on metabolic flexibility. Metabolic flexibility refers to the body's ability to switch between fuel sources, mainly carbohydrates and fat, depending on energy demands. People with poor metabolic flexibility tend to rely heavily on glucose even at rest, which can impair fat loss and contribute to insulin resistance over time. By training in Zone 2, individuals enhance their ability to burn fat as a fuel source both during exercise and at rest. This has significant implications for those aiming to lose fat, as it conditions the body to prefer stored fat over dietary glucose or glycogen. Hormonal regulation is another area where Zone 2 training exerts a strong influence. Regular aerobic training in this zone improves insulin sensitivity, reducing circulating insulin levels and facilitating greater access to stored fat. Lower insulin levels mean that the enzyme hormone-sensitive lipase HSL, which is responsible for breaking down stored fat, is more active. Simultaneously, Zone 2 training increases the activity of lipoprotein lipase in muscle tissue, enhancing the uptake of fatty acids from the bloodstream. These coordinated changes in hormonal signaling amplify the body's ability to use fat as an energy source efficiently. A lesser, known but crucial benefit of Zone 2 training is its effect on autonomic nervous system balance. While high-intensity workouts predominantly stimulate the sympathetic nervous system, the system responsible for the fight or flight response, Zone 2 training supports parasympathetic activity. This improves heart rate variability, promotes recovery, and helps regulate cortisol levels. Chronic cortisol elevation is associated with abdominal fat accumulation and impaired metabolic health, so maintaining a healthy autonomic balance through aerobic work can indirectly support fat loss efforts. Many endurance athletes have long known the value of Zone 2 training, but its relevance extends well beyond competitive sports. For individuals with sedentary lifestyles or those experiencing metabolic dysfunction, such as prediabetes or insulin resistance, Zone 2 provides a safe, sustainable, and highly effective way to recondition the metabolism. Moreover, it is accessible to nearly everyone. Walking briskly, cycling at a moderate pace, or using an elliptical machine can all be performed in Zone 2. It does not require maximal effort, which reduces the risk of injury and makes adherence more likely over the long term. From a practical standpoint, Zone 2 sessions are most effective when performed consistently, typically for durations of 30 to 60 minutes per session, several times per week. The relatively low intensity means that the body can recover quickly from these workouts, allowing them to be incorporated frequently without interfering with resistance training or higher intensity interval sessions. This makes Zone 2 training an ideal foundational activity that supports both fat loss and overall metabolic health. It also serves as a diagnostic tool. As mitochondrial efficiency and cardiovascular conditioning improve, individuals will find that they can maintain a higher pace or power output while staying within the same heart rate zone, signaling improved metabolic function. Sleep optimization is a foundational yet often underestimated element in the pursuit of fast fat loss. While nutrition and exercise are frequently emphasized, the role of high-quality, consistent sleep in regulating metabolic function, hormonal balance, and fat oxidation is profound. The architecture of sleep, including the timing, duration, and depth of various sleep stages, directly affects key systems involved in appetite regulation, energy expenditure, and body composition. One of the primary mechanisms by which sleep influences fat loss is through its effect on appetite regulating hormones, leptin and ghrelin. Leptin, produced by adipose tissue, signals satiety to the brain and helps suppress hunger. Ghrelin, secreted mainly in the stomach, stimulates appetite and food-seeking behavior. When sleep is restricted or of poor quality, leptin levels decrease while ghrelin levels increase, creating a hormonal environment that drives increased hunger and caloric intake, particularly for high-calorie, carbohydrate-rich foods. This hormonal imbalance persists even after just one night of insufficient sleep, which illustrates how quickly sleep loss can begin to derail fat loss efforts. Cortisol, the body's primary stress hormone, also plays a critical role in the relationship between sleep and fat storage. Cortisol follows a circadian rhythm, peaking in the early morning to help mobilize energy and declining throughout the day. However, chronic sleep restriction or inconsistent sleep timing can disrupt this rhythm, leading to elevated evening cortisol levels. This disrupts the natural decline necessary for restful sleep and promotes the storage of visceral fat, especially around the abdominal area. Moreover, elevated cortisol reduces insulin sensitivity, making it harder for cells to uptake glucose, which further contributes to fat accumulation and metabolic dysfunction. Insulin sensitivity itself is intimately linked to sleep quality. During deep, slow wave sleep, one of the most restorative stages, insulin sensitivity improves, allowing for more efficient glucose uptake and utilization. Repeatedly shortening or fragmenting sleep impairs this process, which can lead to insulin resistance over time. Insulin resistance causes the body to store rather than burn nutrients, particularly directing them into adipose tissue. It also inhibits lipolysis, the breakdown of fat for energy. Thus, even in the context of controlled calorie intake, poor sleep can impair fat metabolism and blunt the effectiveness of exercise and dietary interventions. Another important aspect of sleep optimization in fat loss is the influence of circadian rhythms. The body's internal clock governs not only sleep, wake cycles, but also fluctuations in body temperature, hormone secretion, and metabolic activity. Misalignment of sleep timing, such as staying up late and waking late or frequently shifting sleep schedules, disrupts these natural rhythms and has been shown to negatively impact metabolic health. People with irregular sleep patterns, such as shift workers, often experience higher rates of obesity, insulin resistance, and metabolic syndrome, even when controlling for diet and exercise. Aligning sleep with the natural light, dark cycle, going to bed and waking up at consistent times, and avoiding artificial light exposure at night supports circadian rhythm integrity and promotes hormonal conditions favorable for fat loss. Melatonin, the hormone responsible for signaling sleep onset, also has indirect effects on metabolism. It not only prepares the body for rest, but also influences insulin secretion and thermoregulation. Exposure to bright artificial light in the evening can suppress melatonin in production, delaying sleep and compromising sleep architecture. Inadequate melatonin in release is associated with higher nocturnal insulin levels, impaired glucose metabolism, and disrupted fat oxidation during sleep. Simple strategies such as dimming lights in the evening and avoiding screens for at least an hour before bedtime can significantly improve melatonin in secretion and the quality of sleep. Growth hormone, another hormone closely tied to sleep, plays a significant role in fat metabolism. A large portion of daily growth hormone release occurs during the first few hours of deep sleep. Growth hormone stimulates lipolysis and the mobilization of fat stores for energy. Disrupted or shortened deep sleep significantly reduces this hormonal pulse, limiting the body's capacity to access fat as a fuel source overnight. Furthermore, growth hormone supports muscle recovery and maintenance, which is essential for sustaining a high metabolic rate, particularly during periods of caloric deficit. Sleep also influences non-exercise activity thermogenesis, or NEAT, the energy expended through daily movements such as walking, fidgeting, or standing. When sleep is compromised, fatigue often leads to more sedentary behavior and reduced spontaneous movement throughout the day. This decrease in overall energy expenditure can create a subtle but persistent energy imbalance that impairs fat loss progress. In contrast, well-rested individuals tend to move more throughout the day, even unconsciously, which contributes significantly to daily caloric burn. Finally, the psychological effects of poor sleep irritability, decreased motivation, and impaired executive function can reduce adherence to nutrition and exercise plans. Cognitive restraint, or the ability to make disciplined decisions around food and activity, is impaired under conditions of sleep deprivation. This can result in more frequent indulgences, larger portion sizes, and skipped workouts, all of which undermine fat loss goals regardless of intention or planning. 4.0 said, fasted movement expanded up to minimum 600 words and do not add any ending sentence, do not add bullets points, ChatGPT said. Fasted movement refers to performing low to moderate intensity physical activity during a state in which the body has not consumed calories for an extended period, typically following an overnight fast. This period is often characterized by low circulating insulin levels and a hormonal environment that favors the mobilization of stored energy, particularly fat. The concept of fasted movement is grounded in metabolic physiology and has gained increasing attention for its role in enhancing fat oxidation, improving insulin sensitivity, and optimizing energy partitioning in favor of fat loss. Upon waking in the morning after an overnight fast, the body is in a state of glycogen depletion, particularly in the liver, which has a limited storage capacity. Muscle glycogen remains relatively preserved, but blood glucose and liver glycogen are reduced, leading to a hormonal profile conducive to fat burning. During this period, insulin levels are at their lowest, while counterregulatory hormones such as glucagon, cortisol, and norepinephrine are elevated. This hormonal shift activates lipolysis, the breakdown of stored triglycerides in adipose tissue into free fatty acids and glycerol, which are then released into the bloodstream to be used for energy. Engaging in physical movement during this fasted window amplifies the fat burning effect. Low to moderate intensity activities such as walking, light jogging, or cycling performed in this state further elevate norepinephrine levels, a catecholamine that stimulates fat mobilization and increases the availability of fatty acids for oxidation. Because insulin is low, the inhibition of hormone-sensitive lipase HSL, the enzyme responsible for initiating lipolysis, is lifted, allowing for greater access to fat stores. Additionally, the reduced availability of glucose during fasted movement encourages the body to rely more heavily on fat as a fuel source, making this window highly efficient for targeting stored adipose tissue. Fasted movement also influences mitochondrial function. Mitochondria are the cellular structures responsible for converting fuel into usable energy. When physical activity is performed in a fasted state, mitochondrial adaptations are triggered that enhance their efficiency and capacity. Over time, this results in increased mitochondrial density and improved fat oxidation capability, both of which contribute to a greater resting metabolic rate and more efficient fuel utilization. The body becomes metabolically flexible, better able to switch between using carbohydrates and fats depending on availability and energy demands. Another important benefit of fasted movement is its impact on insulin sensitivity. Repeated bouts of fasted activity, especially when combined with caloric control and nutrient timing, have been shown to improve the muscle cell's ability to uptake glucose in response to insulin. This increased insulin sensitivity means that less insulin is required to manage postprandial blood sugar levels, reducing the likelihood of fat storage and improving overall metabolic health. Since elevated insulin is associated with the inhibition of fat breakdown, maintaining lower baseline insulin through improved sensitivity supports the body's ability to access and utilize stored fat more effectively. There is also a neurological component to fasted movement that reinforces its benefits. The mild stress of fasting combined with light exercise induces the release of brain-derived neurotrophic factor BDNF, a protein that supports cognitive function, learning, and memory. BDNF also enhances synaptic plasticity and has been shown to improve mood and motivation. This neurochemical response can create a positive feedback loop whereby morning movement improves focus and energy throughout the day, thereby encouraging consistent physical activity and dietary discipline, both critical for sustained fat loss. Furthermore, engaging in movement while fasted can improve hepatic glucose output regulation. The liver plays a central role in maintaining glucose homeostasis, particularly during fasting periods. Fasted exercise sensitizes the liver to signals from glucagon and other hormones, fine-tuning its ability to release glucose when needed without overcompensating. This improves glycemic control and reduces the risk of erratic blood sugar fluctuations, which are often linked to increased hunger and subsequent overeating. From a practical standpoint, the type and intensity of movement matter. Low-intensity aerobic activity is ideal for maximizing fat oxidation during a fasted state. Activities such as walking at a moderate pace for 30 to 60 minutes can be highly effective without causing significant muscle breakdown or elevating cortisol beyond beneficial levels. High-intensity training in a fasted state, on the other hand, can be counterproductive as it relies more heavily on glycolysis and may impair performance or increase muscle catabolism if not properly managed with post-exercise nutrition. It's also worth noting that fasted movement does not need to be exhaustive to be effective. The consistency of daily or near daily practice has a cumulative impact on fat metabolism, especially when paired with a structured sleep schedule and circadian aligned eating patterns. Over time, fasted movement becomes a low effort yet high return metabolic stimulus that enhances overall energy balance and supports the body's natural inclination toward fat utilization in the early part of the day. The psychological benefit of starting the day with physical activity, coupled with the physiological shift toward fat burning metabolism, reinforces behaviors that align with long-term fat loss and improved metabolic health. Cortisol is a glucocorticoid hormone produced by the adrenal glands, and it plays a pivotal role in the regulation of metabolism, inflammation, immune response, and the body's reaction to stress. One of its most significant and often misunderstood roles is its effect on fat storage, particularly the way it influences both where fat is stored and how it is mobilized or preserved under various physiological conditions. Understanding the relationship between cortisol and fat storage requires an appreciation of how this hormone interacts with insulin, glucose metabolism, and energy demands during both acute and chronic stress states. In a healthy and balanced physiological state, cortisol follows a diurnal rhythm, peaking in the early morning to promote alertness, glucose mobilization, and energy availability for the start of the day. As the day progresses, cortisol levels decline steadily, reaching their lowest point late in the evening to allow for restful sleep. This natural rhythm supports the metabolic processes that underpin optimal body composition. However, when cortisol is elevated beyond its natural pattern, neither through psychological stress, poor sleep, circadian disruption, or overtraining, it begins to exert a range of effects that promote fat accumulation, particularly in the visceral region. One of the key mechanisms by which cortisol promotes fat storage is through its interaction with insulin. Cortisol increases blood glucose levels by stimulating gluconeogenesis, the process of creating glucose from non-carbohydrate sources in the liver. In response to this rise in blood glucose, the pancreas secretes insulin to facilitate the uptake of glucose by cells. When this cycle occurs repeatedly or chronically, it can lead to elevated insulin levels and a reduced sensitivity of cells to insulin, a condition known as insulin resistance. Elevated insulin, in turn, inhibits the activity of hormone-sensitive lipase, the enzyme responsible for breaking down stored fat, and promotes the activity of lipoprotein lipase, which facilitates fat storage, particularly in adipose tissue. Cortisol also has a direct effect on fat cell differentiation and distribution. It has been shown to increase the differentiation of preadipocytes into mature fat cells, especially in the abdominal region. Fat cells in the visceral area, those surrounding internal organs, are more sensitive to cortisol due to a higher concentration of cortisol receptors, particularly the glucocorticoid receptor. This makes visceral fat more likely to expand in response to chronic cortisol exposure. Visceral fat is metabolically active and produces inflammatory cytokines, contributing to systemic inflammation and further disrupting hormonal balance. The presence of high levels of visceral fat is not only aesthetically undesirable, but also associated with increased risk of cardiovascular disease, type 2 diabetes, and other metabolic disorders. During periods of acute stress, the body mobilizes energy resources in preparation for physical exertion, a response that was evolutionarily beneficial in situations requiring immediate action. Cortisol ensures a rapid supply of glucose to the brain and muscles by breaking down protein and converting it into glucose, as well as by stimulating the release of stored glycogen from the liver. However, in modern environments where stress is often psychological and not followed by physical activity, the elevated glucose is not used for movement or energy expenditure. Instead, it circulates in the bloodstream until insulin directs it into storage, primarily as fat. This mismatch between stress signals and physical output is a key contributor to fat accumulation in the context of chronic stress. Sleep deprivation and circadian misalignment are also potent triggers of elevated cortisol. When sleep is inadequate or irregular, cortisol does not follow its normal diurnal pattern. Instead, it may remain elevated into the evening, impairing melatonin release and disrupting sleep quality further. This creates a vicious cycle where poor sleep raises cortisol and high cortisol impairs sleep, both of which contribute to fat gain. Additionally, sleep restriction is linked to increases in ghrelin and decreases in leptin, two hormones that regulate hunger and satiety. This hormonal shift can drive increased food intake, particularly of calorie-dense and sugary foods, which compounds the metabolic effects of cortisol. Exercise is another factor that modulates cortisol levels. While acute bouts of exercise, especially high-intensity training, do raise cortisol temporarily, this is typically followed by a compensatory drop and increased sensitivity to insulin, provided recovery and sleep are sufficient. However, excessive training without adequate rest, commonly seen in individuals pursuing rapid fat loss, and lead to chronically elevated cortisol and impaired recovery. This state of overreaching or overtraining reduces performance, increases injury risk, and paradoxically leads to fat retention, particularly in the abdominal area. Strategic modulation of training volume, intensity, and recovery can help regulate cortisol and optimize body composition outcomes. Dietary habits also influence cortisol regulation. Prolonged fasting, very low carbohydrate intake, or caloric restriction, especially in the absence of dietary fat and protein, can increase cortisol as the body attempts to maintain blood glucose levels through increased gluconeogenesis and stress signaling. While brief fasting periods may be beneficial for metabolic flexibility, chronic energy deprivation without adequate nutrient support may create a stress burden that offsets any potential fat loss benefits. Nutrient timing, macronutrient balance, and overall caloric adequacy all play roles in modulating cortisol responses to food intake. The psychological perception of stress also modulates cortisol release. Two individuals exposed to the same external condition may experience vastly different cortisol responses depending on their mindset, emotional resilience, and coping mechanisms. Practices such as mindfulness meditation, breath work, and exposure to natural light have been shown to reduce cortisol and support a more adaptive stress response. These tools are not only beneficial for mental well-being, but also create a physiological environment more conducive to fat loss. Non-exercise activity thermogenesis, commonly referred to as NEAT, represents the energy expended for everything we do that is not sleeping, eating, or formal exercise. This includes the calories burned through actions such as walking to the kitchen, standing while working, fidgeting, gardening, doing chores, taking the stairs, and even maintaining posture. NEAT is a major component of daily energy expenditure and can vary dramatically from person to person, often accounting for hundreds of calories burned each day without structured workouts. In the context of fat loss, NEAT plays a critical role by subtly but consistently influencing energy balance and metabolic function. One of the most striking aspects of NEAT is its variability. While structured exercise may contribute around 5 to 10% of daily energy expenditure for most individuals, NEAT can account for anywhere from 15 to over 50% depending on lifestyle, occupation, and behavioral tendencies. For example, someone with a desk job who drives to work and remains sedentary for most of the day will have substantially lower NEAT than a person in a more physically active profession, such as a server, nurse, or construction worker. This discrepancy can result in a difference of several hundred calories daily, which, over time, significantly influences fat gain or loss. NEAT is closely tied to subconscious behavioral responses and is often influenced by both internal and external factors. One such internal factor is energy availability. When calorie intake is reduced during a fat loss phase, the body naturally attempts to conserve energy. One way it does this is by reducing spontaneous physical activity and NEAT. People may unknowingly fidget less, blink less, take fewer steps, or choose the elevator instead of the stairs. These micro decisions are regulated at a neurological level, often outside of conscious awareness. This phenomenon can partly explain why fat loss plateaus occur even when diet and formal exercise remain constant. The body's attempt to maintain homeostasis results in a downregulation of energy expenditure through reductions in NEAT. Hormonal factors also modulate NEAT. Leptin, a hormone produced by fat cells, plays a critical role in signaling energy sufficiency to the brain. When body fat levels decline and leptin levels drop, the brain interprets this as a state of energy deficit. This can lead to increased hunger, reduced reproductive function, and decreased motivation for physical movement. A reduction in NEAT is part of this adaptive response. Conversely, when energy intake is abundant and leptin levels rise, individuals tend to move more, even without structured exercise, contributing to higher spontaneous physical activity. This feedback loop helps regulate long-term energy balance, but can become dysregulated in chronically sedentary lifestyles or when fat loss is pursued too aggressively without adequate strategic breaks or refeeding periods. Cortisol, the primary stress hormone, can also influence NEAT. Chronic stress often leads to mental fatigue, decision fatigue, and emotional exhaustion, all of which reduce the likelihood of spontaneous movement. When the body is under psychological stress, it may prioritize energy conservation in anticipation of perceived threats, thereby dampening motivation to move. At the same time, individuals under stress may gravitate toward passive coping behaviors such as prolonged sitting, screen time, or comfort eating, further reducing NEAT and promoting fat accumulation. Environmental and social contexts further shape NEAT behavior. Urban living tends to encourage more movement through walking, commuting, and climbing stairs, whereas car-centric suburban or rural environments may limit opportunities for incidental movement. Access to walkable neighborhoods, standing desks, or active commuting options like biking or public transit can significantly increase NEAT without requiring additional willpower or time set aside for formal workouts. Similarly, cultural norms around sitting versus standing, communal eating habits, or the use of manual labor in daily tasks can modulate baseline NEAT across populations. Sleep quality and circadian rhythm alignment also impact NEAT. Poor sleep reduces daytime energy and cognitive function, leading to lower motivation to move and reduced spontaneous physical activity. A well-rested individual is more likely to engage in small movements and decision-making that promotes activity throughout the day. Conversely, fatigue from inadequate sleep tends to result in greater periods of sedentary behavior, which lowers overall daily energy expenditure. This dynamic creates a reinforcing cycle where inadequate rest contributes to lower NEAT, reduced fat oxidation, and impaired appetite regulation, further complicating efforts toward effective fat loss. NEAT can be enhanced through both behavioral strategies and environmental design. Encouraging regular movement breaks during sedentary periods using wearable step counters, choosing to stand or pace during phone calls, and incorporating daily tasks that involve manual labor all contribute to increasing total daily NEAT. Importantly, these activities do not typically induce the physical stress or recovery demands associated with high-intensity exercise, making NEAT a sustainable and low-barrier tool for increasing caloric output without compromising recovery or hormonal balance. The cumulative effect of NEAT becomes particularly significant when aiming for fat loss over extended periods. Even modest increases in NEAT, such as walking an extra few thousand steps per day, and lead to meaningful changes in body composition over time, especially when maintained consistently. Unlike structured workouts that require scheduling and motivation, NEAT operates in the background, influencing metabolism subtly but persistently.